A quick point about stardust, which we all are made of. This is on page 187. When the central hydrogen has all reacted to form helium, 5 or 6 billion years from now, the zone of hydrogen fusion will slowly migrate outward, an expanding shell of thermonuclear reactions, until it reaches the place where the temperatures are less than about 10 million degrees. Then hydrogen fusion will shut itself off. So this is like talking about the sun in terms of being like an oven. Meanwhile, the self-gravity of the sun will force a renewed contraction of its helium-rich core and a further increase in its internal temperatures and pressures. I guess it's actually heating up. The helium nuclei will be jammed together still more tightly, so much that they begin to stick together, the hooks of their short-range nuclear forces becoming engaged despite the mutual electrical repulsion. The ash will become fuel, and the sun will be triggered into a second round of fusion reactions. This process will generate the elements carbon and oxygen and provide additional energy for the sun to continue shining for a limited time. So this process, these ovens is like cooking, or ovens, the stars out there. And of course, eventually these stars, they cook what they have, and then they have to cook other stuff, so they get hotter and more condensed, and eventually they explode. And when they explode, they fire out all the elements that they've cooked together. They start with all this hydrogen. There's tons and tons and tons of hydrogen in the universe compared to everything else. It's the simplest atom. And once these are cooked together, making helium, and then helium combining into other things like carbon and oxygen, etc., and all the other elements eventually are cooked together, of course, but at lower and lower amounts. And eventually these stars compress as they're cooking less and less stuff together to make bigger and bigger atoms. And then eventually they explode and send out their products, which land on planets and, of course, fuel life in some circumstances. Yeah, and he reiterates this on page 190. The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We are made of star stuff. And this is neat. And for an example of an exploding star, apparently one happened, it says, a couple centuries ago. The Crab supernova. It says, this remarkable star, 5,000 light-years distance, is now called the Crab supernova because an astronomer centuries later was unaccountably reminded of a crab when looking at the explosion remnant of through his telescope. The Crab Nebula is the remains of a massive star that blew itself up. The explosion was seen on Earth with the naked eye for 3 months. Easily visible in broad daylight, you could read by it at night. I think that's pretty neat. So that was a few centuries ago, it said. So the Crab supernova, you might want to look that up if you're interested. And this is kind of neat. This is like the biology of stars, I mean, if that makes any sense. Since such stars with higher temperatures and pressures run rapidly through their store of nuclear fuel, their lifetimes are much shorter than the sun's. A star tens of times more massive than the sun can stably convert hydrogen to helium for only a few million years before moving briefly on to more exotic nuclear reactions. Thus, there is almost certainly not enough time for the evolution of advanced forms of life on any accompanying planets, and it will be rare that beings elsewhere can ever know that their star will become a supernova. If they live long enough to understand supernovae, their star is unlikely to become one. So again, I guess there's this right size that's your star in your solar system needs to be. Otherwise, if it's too big, it burns itself out faster, and then it supernovas. And when it supernovas, it basically wipes out everything in the solar system. And anything out too far doesn't matter anyways, because you can't have life out too far. At least then that we know of, because it'd be frozen. So there has to be this right size so that it lasts a long time. And again, such an argument is what creationists might use to say, well, look, everything's perfect. Everything's perfect for humanity. But that's a silly argument because we wouldn't be here unless things were, quote, perfect, although I don't think things are, quote, perfect. Certainly, life has adapted to what the circumstances are. If circumstances are in which life cannot adapt to it, then it doesn't happen. I suppose that kind of argument may then limit what kinds of life would be possible on other planets. It reminds me, actually, I recently finished Childhood's End by Arthur C. Clarke, and I'll do another review of that. And he mentions that, just as an idea, that on planets that have massive gravities, there could be life, but it would be your height. I think the creatures that lived on this planet were like 2 inches tall, and the hills and mountains were almost non-existent, because eventually the energy required to grow beyond a certain point, it's not worth it under heavy gravity. Now, the contrary point is also interesting. A planet that has very low gravity, first of all, may not be able to hold an atmosphere, so that's one problem. That's one limit. But secondly, the lower the gravity, the more likely you're going to have creatures that fly, because it's easier to fly. However, to fly, you also need a pressure, which a pressure would seem to me to be, again, inimical or contrary to a low gravity planet. A low gravity planet will have problems holding air, holding an atmosphere and holding air in it, if it's low gravity. Higher gravity will be able to hold a lot of air pressure to it, although it also crushes everything on the planet. So